Hi everyone, I'm Greg Stitt from the University of Florida. Welcome to the first presentation in a series of training videos for performing timing closure and optimization on field programmable gate arrays. These training videos will be presented to allow you to follow along on the Intel FPGA Dev Cloud, or alternatively, you can apply the concepts and examples to tools from other FPGA vendors. So one of the first things you do when creating an FPGA application is to specify the timing constraints of your design. Now in practice, this can mean a lot of different things, but to keep it simple, in the most basic case, this corresponds to requesting a specific clock frequency for your design. Once you've specified this timing constraint, your synthesis tool can then generate an FPGA circuit and verify that that circuit meets all of those timing constraints using something called static timing analysis. Basically, the synthesis tool and the static timing analyzer verify that your design can actually run at your requested clock frequency. Now, if any of your constraints aren't met after static timing analysis, this means you have to perform timing optimization, also known as timing closure. Basically, you need to improve the timing characteristics of your design until all constraints are met, at which point it is said that your design meets timing or closes timing. In general, this is a very difficult problem that is very time-consuming, which is why it is the topic of this series of videos. So in this first presentation, I'm going to explain the background material and underlying challenges, and then I will have follow-up videos that explain how to actually go about doing this timing optimization. Also, you should be aware that there are a set of code examples and exercises that follow along with a series of training videos that are available at the GitHub repository that is shown on the slide. Now, before we get into the background material, I want to give you some examples of how you would come up with timing constraints in the first place. Now, the list on the slide certainly isn't exhaustive, but it illustrates the most common situations that I have run into with FPGAs. The first example shown on this slide corresponds to the situation where you are working with an FPGA that has a fixed clock frequency that you can't change. So in this case, your timing constraint would be based off of that specific clock frequency. Essentially what you're doing is telling the synthesis tools that after placement and routing, I need to guarantee that my design can run at least at this specific clock frequency. A second example would be when working with an application that has real-time requirements. Let's say, for example, that you have a signal processing circuit that must produce outputs every 1,000 cycles while processing 44.1 kilohertz audio. So this means that we have to have 44.1 thousand outputs every second, which means we need to have a clock frequency that is 1,000 times faster than that, or 44.1 megahertz, which would then become our timing constraint. Now, another situation would be when you have a design that has specific bandwidth requirements. For example, let's say you have a circuit with a 32-bit bus, so 4 bytes, and that circuit requires 1.6 gigabytes per second of input bandwidth to achieve the desired functionality, possibly because of other constraints. So in this case, the clock has to be at least 400 megahertz in order to achieve this amount of bandwidth. So that 400 megahertz would then become your timing constraint for the clock in this design. A fourth situation, which is something that I work with frequently, is when you just want to maximize performance or maximize the clock frequency of your design. So in this case, you don't have a specific timing constraint in mind up front. So what you might do is pick an aggressive constraint, perform timing optimization until that constraint is met, and then basically repeat this process until you can't improve the clock frequency anymore. Alternatively, it's also reasonably common to pick an aggressive constraint that you don't expect to actually be met, and then just fall back to whatever clock frequency is actually reported as safe by the timing analyzer. However, the issue with this is if you choose too aggressive of a constraint, the reported frequency by the timing analyzer will often be very pessimistic. And as you can probably imagine, there are many other situations. In fact, you can use timing constraints for anything. They don't have to just be for a clock. And in practice, they tend to get quite complex if you look at certain FPGA boards. So to keep things easy to understand, this presentation is going to limit the constraints to a single clock constraint. The first thing you need to understand before doing any kind of timing optimization is how clock frequencies and periods are determined. So for any set of connected flip-flops, data must arrive at each flip-flop before the next clock cycle. This means that the clock period essentially acts as a deadline for the delay that can occur between flip-flops. So we'll call this clock period T sub clock, we'll call the deadline T sub deadline, and the delay between flip-flops T sub flip-flop to flip-flop. Now what we want to ensure during timing optimization is that this delay between flip-flops is less than the deadline, where in this case the deadline is the clock period. Now before we go on, you should be aware that this is actually a greatly simplified definition that isn't entirely accurate, but I want to keep things simple at first to make it easier to understand. Now the subsequent slides will gradually add all the actual complexities, so don't worry about that for now. All right, let's take a look at a basic example. So here we have 3 flip-flops and an AND gate. Flip-flops 1 and 2 act as a source for this AND gate, and flip-flop 3 is the destination flip-flop. So if the wires between the flip-flops and the gate have a delay of 1 nanosecond, and the gate has a delay of 3 nanoseconds, then we know that the delay between the flip-flops is 5 nanoseconds. This means that the clock period has to be greater than or equal to 5 nanoseconds, which means that the clock frequency must be less than or equal to 200 megahertz. So we now know that we need to focus on the delays between flip-flops. These delays consist of the summation of 2 different components, cell delays and interconnect delays. A cell is a generic term used to refer to any non-interconnect FPGA resource, so CLBs, lookup tables, RAM, DSP, and so on. Even flip-flops contribute to cell delays, so it's important to realize that flip-flops don't immediately output a value after a rising clock edge. Instead, there is a small amount of time, often referred to as a clock to Q delay, that passes before the output appears. Now, interconnect delays are the delays of all the connections between cells, which includes the FPGA's routing tracks and wires, the connection boxes, the switch boxes, basically all of the components of the FPGA's interconnect. So let's take a look at the example on this slide, where we have a total cell delay of 3.2 nanoseconds, which comes from the 0.2 nanoseconds from the clock to Q of the source flip-flop and 1.5 nanoseconds from each lookup table. Similarly, we have a total interconnect delay of 2.4 nanoseconds, which comes from the delays of the 3 wires. Now, if you're wondering why the wires have different delays, this is very common and results from the router establishing different length paths between the components, either because the placer placed the components different distances from each other, or because of routing congestion. Now, the total flip-flop to flip-flop delay here is the sum of the cell and interconnect delays, which is 5.6 nanoseconds. This means that the maximum frequency for this example is 178 megahertz. One very important thing to be aware of is that there are frequently multiple paths between the same set of flip-flops, and those paths will often have different delays even when using the same set of resources due to differences in the routing of each path. So in these cases, it is critical to focus on the path that has the maximum delay. The circuit shown on this slide illustrates an example of this, where we have 2 paths between the source and destination flip-flops. Now the cell delays of each path here are identical, because they both pass through two lookup tables. However, the interconnect delays of each path are different. The bottom path has a longer interconnect delay of 2.9 nanoseconds. What this means is that we have to consider this longer path when determining the clock frequency. Now, when we sum the cell and interconnect delays of this longest path, we get a maximum delay of 6.1 nanoseconds, which corresponds to a maximum clock frequency of 163 megahertz. Now, if we had only considered the top path, we would have a higher clock frequency, but that wouldn't work because the bottom path would not yet have its data available by the next rising clock edge. So we have to focus on the path that has the longest delay. Now that we have a basic understanding of clock frequencies, anytime that you do timing optimization, what you're ultimately looking for is the maximum clock frequency you can use for your entire design. This frequency is often referred to as Fmax. To determine this maximum frequency, the timing analyzer performs the analysis we just did on the previous slides to identify the longest flip-flop to flip-flop delay across all the flip-flops in the entire design. Now, the path that has this longest delay is usually referred to as the critical path because it is critically important because the length of that path is what determines the clock frequency for your entire design. The example on this slide illustrates this concept using a simple circuit with 3 pairs of flip-flops, each with different propagation delays between them. So the critical path for this example is the path between flip-flop 3 and 4, which has the longest flip-flop to flip-flop propagation delay in the entire design. So this path requires a clock period greater than or equal to 10 nanoseconds, which means that the maximum frequency of the entire design, or its Fmax, is 100 megahertz. Now, it is critically important to remember that despite the fact that the other flip-flop pairs can run faster than 100 megahertz, we need to clock the entire design based on the critical path. Now, there are advanced methods for using multiple clock domains to get around this, but that is well outside the scope of this presentation, where we will focus on a single clock domain. All right, so here is where we start to add real complexities to my original simplified definitions. One thing that original definition ignored is that flip-flops have something called a setup time. This is a small amount of time before a rising clock edge where the input to the flip-flop cannot change. If the input does change during this setup window, the output of the flip-flop becomes what's called metastable, which is problematic and what we want to avoid. It basically means a timing constraint has been violated. Now, the implication of this setup time is that we don't just need data to arrive at the destination flip-flop before the next clock edge. That was the simplified definition we had. We need it to arrive before the setup window of the next clock edge. And this is illustrated at the bottom of the slide. Basically, we need to ensure that the summation of the cell delays and the interconnect delays is less than or equal to the clock period minus the setup time. Now, if these conditions are violated, we have what is called a setup violation. Now, notice this still fits our original goal definition of making sure that the delay between flip-flops is less than or equal to the deadline, but the difference now is that we've redefined the deadline to subtract the setup time from the clock period. So these equations will continue to get more complex and include more variables, but keep in mind, our goal will always be the same. We want to ensure that the delay between flip-flops is less than or equal to whatever our deadline currently is. One more complexity that we have to include for a real design is something called clock skew. So in most timing diagrams that you're used to looking at, the clock signals instantly propagate to all destinations, which clearly isn't physically possible. In addition, clocks are usually extremely high fan-out signals, which makes it impossible to deliver the clock to every flip-flop at the same time. So the inevitable differences in clock arrival times between flip-flops are known as the clock skew. This skew is important because it affects the available time before a setup violation. As shown in the figure at the bottom, a positive skew means that the destination flip-flop receives its clock signal after the source flip-flop. So in this case, the allowable time for the flip-flop to flip-flop delay, which is just the sum of the cell and interconnect delays, is actually increased. This can be seen in the figure because the skew shifts the rising clock edge of the destination clock to a point later in time. When taking skew into consideration, this means that we now need to ensure that the summation of the cell delays and interconnect delays is less than or equal to the clock period plus the clock skew minus the setup time. Now again, this is still the same goal of ensuring that our delay between flip-flops is less than or equal to our deadline, but we've again updated that deadline to now include both the setup time and this new clock skew. Now, one thing to note is that a positive skew actually makes it easier to avoid setup violations because it increases the maximum allowable delay between flip-flops. Of course, a negative skew has the opposite effect, which can be counterintuitive when you're doing timing optimization. One term you will see a lot during timing optimization is slack, specifically setup slack. Now, this setup slack is the difference in time between the setup deadline and the time when data arrives at the destination flip-flop. So again, this deadline is the clock period plus the clock skew minus the setup time, and the data arrival time is the sum of the cell and interconnect delays, which was just the delay between flip-flops. So when the setup slack is less than 0 or is negative for a given path, this means that this particular path has a setup violation and has to be optimized. Now, a positive slack means that that path meets timing constraints, but it is important to realize that there still might be benefits to further optimizing that path. So one example of this is that a large positive slack can help synthesis tools optimize other paths by moving logic around through things like retiming, where operations get moved between different pairs of registers. Okay, on to another real complexity that we have to consider, which is hold times. Hold times are kind of the opposite of setup times. A flip-flop's hold time is a small window of time after the rising clock edge where the input to the flip-flop must not change, or the output will again become metastable. This basically means that new data must not arrive at the flip-flop during this hold window. So mathematically, this means that the sum of the cell and interconnect delays must exceed both the clock skew and the hold time as shown in the figure at the bottom. Or in other words, the total delay between flip-flops must exceed the skew and hold times. So with regards to hold time, the implication of a positive hold is that it increases the minimum delay between the flip-flops. Now this can be very counterintuitive because it means that data arriving at the next flip-flop too fast is actually a problem. Fortunately, this isn't frequently actually a problem, and it's usually something that the synthesis tools will solve for you, but it is important to understand that it can occur. Just like we had a setup slack, we also have a hold slack concept, which is defined similarly. The hold slack is the time between the arrival of data at the destination flip-flop and the hold violation time for that flip-flop. Mathematically, this is equal to the delay between flip-flops minus the sum of the clock skew and hold time. So, like the setup slack, a negative hold slack corresponds to a hold violation. And as mentioned before, hold violations tend to be much less common than setup violations. When they do occur, they are usually caused by clock skew, because an increased skew will decrease the slack. Fortunately, Usually the synthesis, placement, and routing tools will avoid most of these problems for you. All right, so here is a preview of how we will be doing timing optimization. So first, we will be focusing primarily on setup violations since those are more common. Now remember that in order to avoid setup violations, we need to ensure that the sum of the cell and interconnect delays is less than or equal to the clock period plus the clock skew minus the setup time for all paths between flip-flops in the entire design. Now, if that confuses you at all, it is much easier to just remember that our goal is to make sure that the delay between flip-flops is less than the deadline. No matter how complex our analysis gets, this will always be the goal. So now that we know the goal, how do we go about achieving it? Well, first, it's important to realize that the deadline is generally out of the control of the designer. So once you have decided on a clock constraint, this deadline is determined by things almost entirely out of your control. Now, you might be able to affect the skew with super low-level optimizations, but that is not commonly done. So what this means is that our actual timing optimization is going to focus on reducing the delay between flip-flops. Well, we know that this delay consists of two things, cell delays and interconnect delays. So this suggests we have two primary options for timing optimizations. One, reducing the cell delays, usually through some form of logic optimization, and two, reducing the interconnect delays. So that's it for this presentation, but in the next presentation, I will be covering the different bottlenecks that can occur, both in terms of cell delays and interconnect delays, and optimization strategies to eliminate those bottlenecks. Thank you for watching.